Hi, welcome to another IGCSE physics video. In this video, we're looking at section 1.10, part 2, which is kinetic energy and potential energy. In this video, we will learn about efficiency in work that is done, kinetic energy, and we will also learn about potential energy. So let's begin with efficiency in work done. In the last video, we learned that energy or work is a measure of the amount of work that is done. We also learned that energy can be represented by the letter W, or you can also represent it by the letter E, but when we're talking about work done, we use the letter W. And we know that the work that is done is equal to force times the distance for which the force is applied. So in a simple scenario, if you have a box that is lying on a flat ground, and you apply some force required to push it across all that distance represented by the letter X, then the amount of energy that you supplied or transferred to the box from your hands or whatever you're using to push that box will equal to the force times the distance. So let's say if you were to push a box with a force of 100 newtons and you push the box across a distance of 10 meters, we can find the amount of energy that has been transferred to push that box, which is represented by force times the distance for which the box has been traveling. So our work in this case would be 100 newtons times 10 meters, which is the distance for which the box has traveled. And we know that that unit for energy is in joules. So 100 times 10 would be 1000, and our energy would be in joules. So the amount of work that we've done in this case is 1000 joules. From the scenario, we also know that the total amount of energy that had been transferred from this point to this point will always be equal, meaning that the energy at this point was conserved as it should have been conserved after the scenario had been completed. So the law of conservation of energy tells us that in the initial state, the energy would equal to the final state. Now let's talk about efficiency. Efficiency in work is defined as the amount of useful work that is done. If we come back to the scenario that we looked at, we know that this is a perfect scenario, meaning that there's no friction and no energy is dissipated to the surroundings. In this case, all of the energy that we used to push that box had been transferred to kinetic energy to push that box all the way here. But in real life, if you look realistically, does that really happen? Do you always have 100% efficiency in the work that you do? Think about it. In an imperfect scenario, if you were driving a car on some road, whether it was flat or it was rugged, you know that the gravity and the friction from the ground would affect your efficiency in the work that you're doing. Is your engine really 100% efficient? Well, no. Some energy is dissipated to the surroundings. If we look at this imperfect scenario, we know that the energy transfers are not 100% efficient, because this car that is traveling on this ground that is rough, and because of the gravity that is present, the friction that is imposed on the car due to the rough ground, and the air resistance as the car is traveling forwards, causes the efficiency of the work that is done to decrease. So the useful energy output that the car does, that the engine does to push that car forwards, is always going to be less than the realistic amount that you would output if you were in a perfect scenario like this, without any friction, without gravity, or without air resistance. Because energy is lost to surroundings, and therefore energy gets more spread out, or dissipated is another term for it. So in this case, energy is spread out, as due to friction, heat is generated, or thermal energy. And as the car travels, we know that the chemical energy from the combustion in the engine does not completely convert the energy to kinetic energy to push that car forwards. Some of it's also converted to sound energy, which you hear as the car rushes by on the road. So at one point, let's say this car was putting out a useful energy output of 1000 newtons, and its actual capability was about 1500 newtons. Then if we find the rate at which this car is efficient, we find that this car has a very poor efficiency rate of 66%. Now let's talk about potential energy. Potential energy is the energy stored in an object due to its relative position to other objects. Now I know that it may sound wrong or strange that an object's energy may be dependent on its location compared to other objects. Objects more likely to be influenced with greater magnitude have greater potential energy, and vice versa. So what does this mean? Depending on the influencer of the object, for example gravity can determine how much potential energy an object has. In springs, if you compress a spring compared to a spring that is expanded, the compressed spring has more potential energy as it has the potential to expand. It wants to expand. And in gravity, if you have an object that's high compared to an object that's not as high, relative to the ground, then the higher object will have more potential energy, as it has a greater magnitude, as it has more potential or likeliness to fall down with greater magnitude compared to this ball. Another influencer is mass. If you have more mass, then you have greater potential energy. Another one is height. If an object's height relative to another object is high, then that object has higher potential energy compared to one that doesn't have as much height, which will have lower potential energy. So there are many types of potential energy, but in this case we're going to look at gravitational potential energy. So the gravitational potential energy, which is represented by the letter E with the subscript P for potential, is equal to the object's mass times the gravitational field in which the object is being influenced times the height of the object. So let's say you had a bookcase on which you had two balls sitting at different levels of the bookcase. So here on this level, let's say this ball had a height of 5 meters, and this ball that's on the top of the bookcase had a height of 10 meters. So the overall height of the bookcase is 10 meters. And let's say that this bookcase was placed on Earth. So the gravitational constant, or the gravitational field, would be 10 meters per second squared. So using the formula for potential energy, we can find the potential energy of each of these two balls. And by definition, we know that objects that are higher have more potential energy than the objects that are lower, as objects that are lower will fall down with a smaller velocity compared to objects that are higher, which will fall down with a greater velocity as the impact with the ground. So we know that the potential energy of the higher ball would equal its mass times the gravity times height. Let's say that each of these balls have an equal mass of 1 kilogram. So the potential energy would equal 1 kilogram times the gravitational constant, which is 10 meters per second squared, times the height, which is 10 meters. So the potential energy of that higher ball will be 100 joules. Now for the lower ball, again, we know that the potential energy for that ball will be its mass times the gravitational field constant times the height of that ball, which means that we're going to get the mass being 1 kilogram times the gravitational constant of 10 meters per second squared times the height of 5 meters. So in this case, our potential energy will be 50 joules. We can see that height has impacted our potential energy, as the ball that is sitting lower on the bookcase has a lower potential energy than that one that is sitting higher on the bookcase. In this case, we've only experimented with the height affecting the potential energy of the balls. But if we increase the gravity, so if you put that bookcase somehow on Jupiter without it falling in the abyss of the gas giant, then you'd find that the potential energy of these two balls will increase drastically, as the gravitational constant on Jupiter is much higher than that of Earth. Also, if you increase the mass of the ball, then the potential energy will also increase. Now let's talk about kinetic energy. Kinetic energy is the energy of an object simply due to its motion. So if you had a car that was speeding down a road, then you know that that car has some motion. And because it has some motion, we can say that it also has kinetic energy. And kinetic energy is represented by the letter E for energy with the subscript K for kinetic energy. The kinetic energy of an object that has some velocity can be represented by half of its mass times its velocity squared. If we look at the formula, we know that if a car has some velocity and some mass, then if we increase the mass of that object, then the kinetic energy would also increase because of the formula. But if you increase the velocity of that car, if you put your foot on the gas pedal and accelerate the car to a greater velocity, then the car will have a drastically more kinetic energy. And this is because of the velocity that is being squared. So if you increase the velocity, then your kinetic energy will increase exponentially compared to the amount of velocity that you increased. Now let's look at a scenario in which kinetic energy is involved. Kinetic energy and potential energy are often related in different scenarios. Let's say that you have a stationary object like this ball that is sitting on the bookcase. And let's say that it's sitting on top at a height of 10 meters. And let's say it also has a mass of 1 kilogram and the bookcase is sitting on the earth. So the gravitational constant will be 10 meters per second squared. From the law of conservation of energy, we know that energy is never wasted. Energy cannot be created or destroyed, but it can only be transferred. So when this ball falls down, we know that the potential energy of the ball will drop because when you decrease the height, the potential energy will also decrease. But energy cannot be wasted, so there must be a gain in some other form of energy. And that form of energy is kinetic energy, which increases as our velocity increases. So when that ball falls down, the potential energy of that ball will decrease as its height will decrease, and its velocity will also increase as it accelerates towards the earth, so its kinetic energy will also increase. So the potential energy of that ball is being converted to its kinetic energy. From the previous example, we know that the potential energy of that ball when it's stationary at the top of the bookcase is equal to its mass times the gravity times the height. We know that the mass of the ball is 1 kilogram times the gravitational constant, which is 10 meters per second squared, and times the height, which is 10 meters. So when we simplify that, we get 100 joules of energy. By definition of the law of conservation of energy, we know that when this ball falls down, it must gain a kinetic energy of 100 joules. So using the law of conservation of energy, we can say that the kinetic energy of the ball will equal its potential energy as soon as the ball hits the ground here. And we can also find the final velocity right before it touches the ground. We know that the kinetic energy of the ball is 1/2 of its mass times velocity squared, which will equal to the potential energy of 100 joules. We know that the mass of the ball is 1 kilogram, so 1/2 of 1 is just 1/2, times the velocity squared equaling 100 joules. So we can multiply each side of the equation by 2, giving us that the square of the velocity equals 200 joules. And then we can take the square root of each side. We get that our final velocity of that ball, right when it hits the ground, will equal approximately 14.14 meters per second in this direction. And this is it for section 1.10 part 2. There's a link to part 1 if you want to learn about energy. Leave a like if you liked this video and subscribe for more videos in the future. Also leave a comment in the comment section and provide feedback so I can improve my videos in the future. And I'll see you in the next video. Thanks for watching.